Hello everybody, getting ready to do lesson 2.8 part 2 classwork of pre-calculus math today. Email me here for course materials. 2.8 part 2 quadratic models, 0 points in your notebook taking today, 56 points of classwork today. So let's jump right in here to our next example, part 2 of 2.8 part 2. Fitting a quadratic model to data. A basketball is dropped from a height of about 5.25 feet. The height of the basketball is recorded 23 times at intervals of about 0.02 seconds. The results are shown in the table using a graphing utility. Use a graphing utility to find a model that best fits the data. Then use the model to predict the time when the basketball will hit the ground. So here's our table here. We got 0 here, we got height here. So we got like a slow-mo camera here of showing our basketball slowly losing height, 5.23, and then this is our time here in seconds. When we end up down here 0.43, almost a half a second, we're still 1.6 feet above the ground. So begin by entering data into a graphing utility and displaying the scatter plot as shown. So this will be your scatter plot here of this table of data. And then this is 6 feet, and then this is 0.6 seconds over here. So by doing that, from this scatter plot, you can see that the data show a parabolic trend. We have a half parabola here. So using the regression feature of the graphing utility, you can find a quadratic model. That quadratic model that best fits the data is given by this thing here, negative 15.449 x squared minus 1.30 x plus 5. So once we have that, using this model, you can predict time when the basketball hit the ground by substituting 0 for y. So here's our original model, and then we substitute 0 here for y, and then solve for x. Then we're going to use the quadratic model here. So when we plug in values from our quadratic into the quadratic formula, we end up with 0.54. So we have positive solution here. Once we crank this out, this will come out to 0.54. So the solution is about 0.54 seconds, which would be about right here. In other words, the basketball will continue to fall for about another 0.1 seconds before hitting the ground by using a quadratic model for that. So we got our next guided practice here. We have a data set. We're going to create a scatter plot, and it shows the percent of U.S. population who use the internet through 2003 to 2008. And then down here we're going to use a regression feature to come up with a model, a quadratic model for that. So first we're going to plot the data. And then this is what your data would look like here, 2, 4, 6 plots here. And down here the model, once we plug that into your calculator, here is your model for this data set. Then using the graphing utility, graph the model with a scatter plot from part A. So we're going to, once we have our regression, then we go ahead and plot that and see how closely it matches the original plot. Looks like it does a pretty good job. And then according to the model, what year will the percent of U.S. population who use the internet fall below 60%? Is this a good model for making future predictions? So it looks like P equals 60. Determine when the percent of the U.S. population who use the internet falls below 60. Set P equals 60. Using the quadratic formula, solve for. Then we're going to make this equal to 60, and then we're going to solve for t here, the time that we have. And then when we do that, we have 13.54 2014 for the year that it will fall below 60. So Percent of U.S. population using internet will fall below 60% in 2014. This is not a good model for predicting future years. In fact, by 2021, the model gives a negative value for the percentage. So the model really doesn't make any sense, is what it amounts to. So you got to use another model, or your data is wrong. Example 4, choosing a model. We have a table here in gallons per person of regular soft drinks consumed in the United States through 2000, 2007. Here is a data set here. Use the regression feature of a graphing utility to find a linear model and a quadratic model for the data. Determine which model fits the data. So let x represent the year with x equals 0 corresponding to 2000. Begin by entering data into a graphing calculator. Using the regression feature of the graphing utility, a linear model for the data is this. Here's her linear model. And then a quadratic model for the data is this. So we have two models here. So to see which one works out the best, here is your linear model here. And then here's your quadratic model here. So to determine which model fits data better, compare the y values given by each model with the actual y values. The model whose y values are closest to the actual values is the better fit. In this case, the better fitting model is the quadratic. So the quadratic, when you compare from your plot, for your original plot, to your expression that you derive from your regression, it seems like your quadratic model is your better fit. Okay, again, we got another data set. We're going to graph it, create a scatter plot, and then use regression to come up with an equation. Here's the plot. And then this is a linear model for this plot here. And then our R squared number is 0.9469, coefficient of determination. Okay, so using the graphing calculator to graph the linear model with a scatter plot. So we're going to see how well the linear model matches with the original scatter plot. What that looks like here, it looks like it's kind of a fair match there. And then you use the regression feature of the graphing calculator to find a quadratic model for the data and identify the coefficient of determination. So here is our quadratic model, and then our coefficient of determination seems like it's a higher score, so it's closer to 1. So it would make the quadratic model a better fit than the linear model. So using the graphing utility, graph quadratic with the scatter plot, we have this here, which looks pretty good. And then which model is a better fit for the data? The quadratic is a better fit. Answers will vary, but the quadratic is a better fit because your R squared number is closer to 1. So, and then use each model to approximate the year when the number of televisions in homes will reach 350 million. So set t for the model equal to 350 and solve for t. So here's our linear model. So we have 23.1 or 2014. And then using our quadratic model here, making this equal 350, what we come up with here is 20.3 or 2011. So the quadratic model says it's going to be earlier than the linear model does. And that is 2.8 part 2, pre-calculus math. Email me here for tutoring or for instructional materials and video, PowerPoints, etc. Thank you.